Solar panels won. That's not really debated anymore. In many countries today, installing solar is cheaper per kilowatt hour than building new fossil fuel power plants, and millions of rooftops are now generating their own electricity directly from sunlight. So here's the strange part. Despite that, engineers are still trying to reinvent wind power. Not the giant three-bladed turbines you see on wind farms. Smaller systems, stranger designs, some that don't even look like turbines anymore. And every single one is trying to answer the same question. If solar already dominates rooftops, why does wind still exist at small scale? Always do your own research before making any energy investment decision. TESUP Atlas is a residential wind system designed for homes and small businesses. The company behind it, TESUP, operates in the UK and markets compact renewable systems for distributed energy generation. The Atlas system is typically positioned in the up to 10 kilowatt class, depending on wind conditions. That number sounds strong for a home system. But here's the problem. That output only exists under consistent and strong wind conditions, which most rooftops simply do not have. And that creates the first contradiction in this entire category. Because solar panels don't care about turbulence, direction, or wind consistency. They just need light. So Atlas is not really competing with wind farms. It is competing with something much simpler. A flat black panel on your roof that already works almost everywhere. Which leads to the real question. If solar is predictable, why is wind still trying to enter homes at all? The SD6 turbine from SD Wind Energy in Scotland takes a very different approach. This is not experimental design. It is traditional engineering focused on durability. It is rated at around 6 kilowatts with a rotor diameter of about 5.6 meters. That places it firmly in the serious off-grid category. Farms, remote sites, telecom installations. But here's the key tension. Unlike solar, which scales modularly with panels, wind requires perfect placement. A few meters of elevation difference can drastically change output. So even though SD6 is reliable engineering, it introduces a hidden dependency. Location becomes everything, and that creates a major limitation. Because the more precise your energy system needs to be, the harder it is to scale for everyday users. So engineers asked a different question. What if wind could work in cities instead? The Liam F1 turbine, developed by the Archimedes in the Netherlands, is designed for rooftop urban environments. It uses a spiral structure instead of traditional blades. The system is built for small-scale generation in the 1 kilowatt class range. Now that number is important, because it immediately places it below typical household consumption needs. So why build it at all? Because it is trying to solve a problem solar struggles with: urban airflow variability and wind direction changes. But here's the contradiction. Urban environments are exactly where wind is weakest and most chaotic, which means performance is unpredictable. And that leads to the bigger conflict. Cities already have rooftops dominated by solar panels. So Liam is not competing in a vacuum. It is competing for the same physical space. And that makes its survival extremely difficult at scale, which leads to a different idea entirely. Flower turbines are designed in the United States and focus on compact vertical axis wind systems arranged in clusters. Their design allows multiple turbines to be placed closer together without heavy aerodynamic interference. One of the key claims is reduced noise and improved visual acceptance. That matters more than people think, because many wind projects fail not technically, but socially. Communities reject them due to appearance and noise concerns. But here's the tension. Even if turbines become visually acceptable, they still need to compete with solar economics. Because solar has no moving parts, no noise, no spacing conflict. So flower turbines are solving perception, but not necessarily cost dominance. And that leads into harsher environments where solar struggles. IceWind is an Icelandic wind technology designed for extreme environments. Snow, ice, high wind loads, mechanical stress. It uses enclosed vertical axis rotors designed for durability rather than maximum efficiency. This makes it suitable for remote or harsh climates where maintenance is difficult. But here is the key number logic. Extreme durability often comes at the cost of energy efficiency. So you gain survival, but lose output. And that creates a direct conflict with solar again. because solar performs best in clear, stable conditions, which are ironically the same conditions where most humans live. So IceWind only wins in a narrow category, which leads to systems designed for pure independence. AeroMINE is a bladeless rooftop wind system that uses aerodynamic pressure differences to generate electricity. Instead of rotating blades, it channels airflow through a structure that creates pressure zones. The company claims that under certain rooftop conditions, it can achieve energy performance competitive with distributed renewables in constrained spaces. But that claim is important because it is not universal. It is conditional, which immediately introduces uncertainty. And uncertainty is exactly what solar does not have. Solar output is predictable. AeroMINE is situational. So the question becomes, is innovation enough to overcome predictability? Or does predictability always win at scale? That question leads to the most extreme redesign of wind itself. But this brings us to a much deeper realization about the physics of clean energy. Every single wind system we have looked at, whether it spins, vibrates, or flies, shares a fundamental limitation: kinetic energy. To capture wind power, something physical has to move. And when physical things move, they encounter friction. They encounter mechanical wear. They require regular maintenance. They require bearings, generators, and physical space to operate. Solar panels, on the other hand, operate on an entirely different layer of physics. Photovoltaic generation is completely solid state. It is a chemical reaction to light. No moving parts, no physical friction, no mechanical failure points. This is the hidden asymmetry between these two technologies. Wind engineering is a constant battle against physical degradation. Solar engineering is simply a matter of manufacturing scale. And that structural difference explains exactly why small wind faces such a steep uphill battle. It is not just competing with a different product. It is competing with a simpler law of physics. Which brings us back to our final question. Before the final verdict, there are other radical concepts trying to break the mold. Systems like Primus wind power for marine survival, Vortex Bladeless utilizing vibration instead of rotation, and Airborne wind using high-altitude kites. But they all face the same ultimate reality. After looking at all these systems, one pattern remains consistent. Every wind innovation is solving a real, specific problem: noise, space constraints, wildlife impact, or extreme environments. But none of them remove the core constraint of the medium. Wind is variable. Solar is predictable. And in our current energy landscape, predictability is the metric that wins. So the real question isn't which turbine is best. It's whether engineers are truly improving wind or simply trying to force it to compete where it was never meant to go. Because if solar has already solved the simplest version of the problem, the future of wind power may not be replacement. It may only be specialization.